Okay, so we can start, George.
Yeah.
And so today's speaker is George Willis, and he will talk about scale groups. So welcome, George.
Yeah, George doesn't require to be introduced because he's very famous in our department. But in any case, he's great commutation from Australia. He visited us a couple of years ago and maybe in the past many times. So please, George.
Okay, well, thank you very much for that introduction and those kind words. I'd like to speak today about scale groups, and so here is an overview of what I want to say. I'm not going to talk about everything on this table, but let me just say a little bit about what I am going to say and what is on this table. So this should be read as follows. If you look at the first row here, I didn't do that. Look at the first row here. These are various classes of abstract groups here. So Lie groups or topological groups or just profinite groups. And here we're talking about finitely generated discrete groups. So there are various classes of abstract groups on the first row of this table. And on the second row is it's talking about various concrete representations of some of these groups as acting on trees. And I'll speak about some of this in more detail later and during the talk. But the second row is representations of some of these abstract groups on trees. This is generally theorems as part of the structure theory of these groups, tells you that they can be represented as acting on trees. And then in the third row, here we have groups acting on trees, but there's some labeling of the vertices of the tree. This pen is not working all that well, I see. But there's some labeling of the vertices of the tree. And that's used to make explicit computations in the group. Now, here's an overview of what I'm going to say. The first section is, well, it's just overview. This is more or less what I've just done, explaining explaining that table, and I'll return to that table throughout the talk. But then there's the next three sections are really going to be the bulk of the talk. I'll begin by saying something about general totally disconnected locally compact groups. So these are the groups that are these groups that are on the first row here and in the middle column of this table. After that, I'll say something about the tree representation theorem, that is representations of some of these groups as acting on trees. And this is where the notion of scale group will come in. The next part is probably the longest part of the talk. And there I'll be talking about specific labellings of the vertices of the trees and a correspondence then between scale groups and self-replicating groups that comes about through those labellings. And then at the end, I'll say something about the uniqueness of these different representations of the groups. So let me begin now with so this is the second section. This is to do with totally disconnected locally compact groups and notions of scale and tidiness for these groups. So the starting point of the structure theory of totally disconnected locally compact groups is a theorem of Van Danzig that was proved in the 1930s. And he showed that if we have such a group, totally disconnected and locally compact, and a neighborhood of the identity of such a group, then there is some compact open subgroup that's contained in that neighborhood of the identity. So another way of saying that is that totally disconnected locally compact groups have small compact open subgroups. And I'm going to be talking about the compact open subgroups quite a bit, so I'll have this notation for the set of all compact open subgroups of the group. And this theorem has the corollary that I'm not going to be using it explicitly, but it's good to keep it in mind, that every compact totally disconnected group is profinite. And conversely, every profinite group is also a compact totally disconnected group. So that's the basic results for totally disconnected locally compact groups. Now, based on that is the notion of the scale of an endomorphism of a group. So suppose that we have some totally disconnected locally compact group and some endomorphism. So it's a continuous homomorphism of the group to itself. Then this endomorphism has a positive integer associated with it called the scale. And the scale is the minimum of all these indices. If I hold this still, it's better. So what we do is we apply our endomorphism to a compact open subgroup U. So this is now a compact group. It might not be open. And then we consider the intersection of our original compact open subgroup with this image. So this will now be an open subgroup of a compact group. And so this index is finite. So for each compact open subgroup, we have some positive integer computed in terms of the endomorphism and that compact open subgroup. It's just this index. And the scale of the endomorphism is just the minimum of all those positive integers. And then we'll say that any compact open subgroup at which the scale is attained is minimizing for that endomorphism. And in the case when our endomorphism is in fact an inner automorphism, this scale induces another function from the group to the positive integers, where we just define the scale of the group element to be the scale of the inner automorphism that it induces. And this is then the scale function on the group G. So this is the scale of an endomorphism in the first place, but also it induces a function on the totally disconnected locally compact group G. Now, it's the case that not just a positive integer, but a group may be associated with alpha. And that's what I'm going to talk about next. So with each endomorphism, we can actually associate some groups with that endomorphism. And this group acts by automorphisms on a tree. So that's what I'm going to talk about next. So how does this group come into the picture? Well, it comes in through this theorem which characterizes the minimizing subgroups. It tells us which groups are minimizing by the structure of those groups. So again, we take our endomorphism alpha and some compact open subgroup, and we define two subgroups, U plus and U minus. Now, U plus is the set of all elements of U, so it's a subgroup of U, and it's all elements such that if we that element sort of has a history inside U. So we can find some sequence inside U such that alpha of UN plus 1 maps to UN. So the inverse image of U under alpha might not be unique because alpha is an endomorphism. It might not be one-to-one, but we can find some sort of trajectory within the subgroup U, which is left invariant by alpha and which terminates at our given element U. So U plus is a set of elements of U that have a history inside U as we iterate alpha. And U minus is a set of elements of U such that as we apply alpha, we stay inside U. So these are the elements whose future lies in U. So U plus is the elements whose past lies in U, and U minus is the set of elements that whose future lies in U. And these are both closed subgroups of our compact open subgroup U. And then it turns out that U is minimizing if and only if two conditions are satisfied. The first is that U should be the product of U plus and U minus. And the second is that U double minus, which is defined to be this union, that union is closed. Now, the inverse image of a group is a group. And as we increase n here, this is an increasing set of subgroups of G. And so this union is automatically a group, but the condition is that it should be a closed group. And when these two conditions are hold, the scale of alpha is just the index of U plus in alpha of U plus. You see alpha expands U plus and shrinks U minus. So that's the characterization of minimizing subgroups. And as a definition, we'll say that U is tidy above for alpha. So this is TA is tidy above. If U satisfies TA, it's tidy above for alpha. And if it satisfies TB, it's tidy below. And if it satisfies both, we'll say that U is tidy for alpha. So a couple of examples. We could take our group to be the SL2 of the p-adic numbers, and alpha to be conjugation by this diagonal matrix. Then the subgroup U plus, consisting of all matrices that have p-adic integer entries, but in the top right corner, that entry has to be a multiple of P. This subgroup is tidy for alpha. And U plus is then the group of lower triangular matrices, and U minus is the group of upper triangular matrices in U. And the fact that U is in the product of U plus and U minus is just a statement that U factors into lower triangular, a product of lower triangular and upper triangular matrices. We need to have the multiple of P here in the top right corner in order to allow that to happen. If we just had allowed all integer entries, then we wouldn't have this factorization property, because there's a matrix, say we had 1 minus 1 here, then and 0, that would be an integer matrix, and its determinant is 1, but it doesn't factor into upper and lower triangular matrices. So that's why we require the multiple of P in the corner here. And our U double plus, sorry, is the subgroup of all matrices with 0 on the top right corner, integer entries on the diagonal, and any p-adic number in the lower left corner. And U double minus is the group of all upper triangular matrices with integer entries on the diagonal, and any p-adic number in the top right corner. And the scale is P in this case. So that's an example of a p-adic Lie group, and this example is fairly typical of Lie groups over p-adic numbers or a field of formula rod series. Now, for another example, we could take our group to be the group of automorphisms or isometries of a regular tree, and alpha to be conjugation by some element of the group. So here's alpha, it's just an inner automorphism of the group. And if this element G happens to fix a vertex of the tree, then alpha, in fact, leaves invariant the stabilizer of that vertex. And this is a compact open subgroup, and so the scale is 1 in this case. So that's if G fixes a vertex of the tree. If G fixes an edge of the tree, then again, there is some compact open subgroup that's left invariant by alpha, and the scale is again 1. And the third possibility for G is that it translates some axis through a distance D. Now, I should say that it's a theorem of Jacques-Tits from 1970 that every automorphism or every element of our group G is one of these 3 types. So these 3 statements here cover all the possibilities for elements of the group. And the third type then is if we have some translation along some axis. So here is our axis, and the element G translates that axis through some distance. So that's a translation of our regular tree. Here we have, in this example, we have Q equals 2, so every vertex has degree 3. So a tidy subgroup then is found by, say, choosing 2 vertices on this axis and letting U be the intersection of the stabilizers of those vertices. Then this U is tidy for alpha, and the scale is Q to the D, where D is the distance through which the axis is translated. Now, I could say a little bit about what U plus is. So if alpha is translating through some distance D, say, then U plus will fix every vertex to the right of V1 and V2. So U plus fixes all those. And let's perhaps go to a different color. U minus fixes every vertex to the left of V1 and V2. And it's not hard to see that, U then is the product of U plus and U minus, and that U double minus is closed. Because U double minus is the, perhaps I'll say, U double minus is the fixator of an end, which I'll call infinity, and I think this end is out here. So here is our end infinity. U double minus fixes this end of the tree, and that fixator is a closed subgroup of the group. So that's the scale and automorphisms of trees. So I've now covered this part of the table, and next I want to say something about this section. So the relationship between general totally disconnected locally compact groups, or at least between the scale and tidiness, and a representation on a tree. So here the theorem is the relevant theorem is the following one. So we suppose now that we have some compact open subgroup U that's tidy for an automorphism now. So this is a statement for automorphisms, not for endomorphisms. There is a statement for endomorphisms, but it's a bit more complicated, and so I'll just stick with automorphisms here. So if alpha is an automorphism and U is tidy for it, and we let U double minus be this closed subgroup, then U double minus is invariant under alpha. So alpha of U double minus is equal to U double minus. And we can form now the semi-direct product between U double minus and the group generated by alpha. And the theorem says that this group acts on a regular tree, T sub Q plus 1, where Q is the scale of alpha inverse. And the image of this group under this action is a closed subgroup of the isometry group of the tree, and it fixes an end of the tree, and it's transitive on the vertices of the tree. And the kernel of the representation is the largest compact normal alpha invariant subgroup of U double minus. Now, one proof of this just refers to the idea of an H&N extension and Bass-Serre theory. So the automorphism alpha maps U minus into itself, just that follows automatically from the definition of U minus, if this is the case. And so alpha is an endomorphism of U minus into itself. And the index of alpha of U minus in U minus is this number Q, the scale of alpha inverse. And then the Bass-Serre, well, this is the definition of what it means. No, sorry. There is a group called an H&N extension that is produced by this situation, and then the Basset theory says that this group acts on a tree. So that's one way to see that this theorem holds, but another way is perhaps more direct, is to define directly what the vertices and edges of the tree are. So we can define the vertex set of the tree to be just a set of all cosets of the group over the subgroup U minus. So U minus is going to fix the vertex in the tree, and then the set of all vertices, since the group is transitive on the vertices, is going to be given by this coset space. And then the edges are defined as pairs of vertices as follows. So that's the tree representation theorem. Every group of the form U double minus semi-direct product alpha acts as a group of automorphisms of the tree. Now, here's a picture of what's going on here. So here we have the tree in the case where, again, Q is 2. And if we consider all of the cosets of the form, say, U double minus mod U minus, these are all cosets here above U minus, and all the cosets of the form, say, U double minus alpha squared U minus, these are all above this vertex alpha squared, this coset alpha squared U minus. So these are the vertices of the tree seen as cosets of the group over U minus. And these cosets of the form U double minus alpha NU for fixed N, these are called horospheres in the tree, and they are clearly invariant then under the subgroup U double minus, and they're translated by the action of alpha. So alpha will translate one horosphere to the next one. I guess this is alpha squared that I've got drawn a picture of. So alpha squared will translate this horosphere to this one. So that's one way of seeing the tree on which the group acts. Now, we come to the definition of a scale group, which is the subject of this talk. So a scale group now is just any group of automorphisms of a regular tree that satisfies the conclusions of that theorem. So it fixes an end of the tree, it's transitive on the vertices, and it's a closed subgroup. So a closed subgroup of the automorphism group fixing an end and transitive on the vertices is a scale group. Now, here are some examples. The automorphism group of the regular tree fixing an end, or the subgroup of the automorphism group that fixes an end, this is an example of a scale group. Another example is the group of p-adic integers under addition, semi-direct product, the multiplicative group of that field. This is an example of a scale group. It can be represented as acting on a tree, and the nth horosphere is in a set of cosets QP mod P to the n of the p-adic integers. So the p-adic integers fix the vertex in this tree. And then there's a similar example where instead of the p-adic numbers, we take the field of formula Laurent series over some finite field. So these are examples of scale groups. Now, so I've now talked about this part of the table. Are there any questions so far?
Do you have zoo in your house?
No, I don't, but we have a few birds outside, if that's what you're hearing.
They started to assist you when you started to speak about mathematics. But it's okay. It's okay.
They must be interested too. I've gone quiet for now, but we might hear them again later. Okay, so let me come now to the next part of the talk, I now want to say how, talk about this part of the table. So this is the third part of the talk, how scale groups, so scale groups act on trees, but now we can define a specific labeling of the tree in terms of the scale group. So here is how we do it. So we suppose now we just have some scale group acting on the tree, and the infinity is an end fixed by the group. Now, there isn't a translation of the tree that is contained in our group G. This is a consequence of the transitivity of the scale group on the vertices. There is some translation that goes through distance 1, and that has alpha as a repelling end. So we'll choose such an alpha, and then we'll choose some vertex whose axis passes through V, that vertex V, or some vertex that lies on the axis. And then we'll define U tilde to be the set of all elements of our group, our scale group, such that G is elliptic. So G is elliptic means G has finite orbits. In its action on the tree. You see the translation, alpha does not have finite orbits. It obviously has an axis, but there are elements that fix a vertex or an edge, say, and these will all have finite orbits, and these are what we call elliptic elements, and these in fact form a closed subgroup of G, and we'll call that closed subgroup U tilde. Then it can be shown that G is a semi-direct product of U tilde and the group generated by alpha. And I'll abbreviate that just as U tilde alpha, just to save a bit of space and save a bit of writing. And U then is tidy for alpha. So our U is the stabilizer. We'll take U to be the stabilizer of the vertex V. And U is tidy for alpha. And U double minus is U tilde. And U plus is in fact a subgroup of U. So that's what we have from any scale group. And now we can use this to define a labeling of the vertices of the tree. And we're going to do that by choosing coset representatives of the coset space U mod alpha U. So I'll say more about this on the next slide. So here is our full tree. I've drawn it slightly differently now, but we have a particular vertex that I'm now labeling by U. This is the vertex that we called V before. Now I'm labeling it by U because U is the stabilizer of that vertex. And if we choose coset representatives, so we'll call them U0 is just the identity, and then there are Q minus 1 other representatives. These are coset representatives for this quotient space, and this set of cosets has order Q because well, that's the valency of the tree on which U acts. Sorry, Q plus 1 is the valency of the tree on which U acts. Then Uj alpha, they represent the cosets below U, where now we're thinking of below is further away from the point infinity. So below means with respect to the point infinity, which is out in this direction. So this is the vertex that's fixed by our scale group. And then alpha U up to U sub Q minus 1 alpha U. These are the stabilizers of the vertices below U, and we'll label our vertices with those cosets. And then on the next level, we have representatives of this form because see, if we apply alpha, alpha pushes our alpha pushes our tree down in this direction. And so alpha pushes alpha u down to alpha squared u, and it pushes alpha 1 u down to alpha 1 u alpha squared u. So our translation pushes our tree down by distance 1. And so we have labels alpha squared u and alpha 1 u, alpha squared u for these two vertices. And then we have labels u1 alpha squared u and u1 alpha 1 u alpha squared u for these two vertices, and so on. So we can label all of the vertices according to the coset, or we can choose coset representatives for all of these vertices below the vertex u or v. Now, we can abbreviate this a little bit. Instead of taking this coset representative, we'll just abbreviate this by the string j0 up to jn-1. So these are the subscripts on the coset representatives here. So we can now associate a string in the set 0 up to q-1 with each vertex. So that's what we have now in this picture. So we're now labeling the vertices below our original vertex v. I'm now using a dot, I guess, and sometimes we could use an empty set to label that vertex. But then all the vertices below that in this rooted tree are labeled by strings. Now, by construction, uj maps the vertex 0 to the vertex 1, and it copies the tree below 0 to the tree below 1, and it, simply by changing the first symbol in the string from 0 to 1, all the other symbols stay unchanged. And alpha translates this tree, which I'll denote as t sub dot, identically to the tree below 0. So it translates this tree to this tree simply by putting a 0, by adding a 0 to the first place of every string. And not only that, but alpha of u stabilizes the vertex 0, and the group of automorphisms or isometries of this tree is conjugated to the group of isometries of this tree by alpha. And what else did I want to say? Right. Yes. I haven't gone through the full description of the labeling of the full tree, but we can in fact extend this labeling to the entire tree, and we see that for any two vertices in the tree, there is some element of our scale group that maps the tree below v to the tree below w and preserves the labeling. And in particular, the tree u restricted to this subtree is a closed subgroup of isometries of the rooted tree, and it satisfies this definition. And this now is a definition of a self-replicating group. So we suppose we have some group of isometries of a rooted tree with the vertices labeled by strings in some Q symbols. Then G is a self-replicating group if it's transitive on level 1 of the tree. And the isometry that, well, if we take our element G and we look at what G does to a vertex, to the tree below a vertex V, then that will give us an automorphism of our tree again, and that automorphism should belong to G. And conversely, for every element of the group, and vertex V, there is some element of the group such that H acts below V, just like G. So these two conditions are that every element of the group, and for every element of the group and every vertex, the element acts below that vertex just like an element of the group. And the other statement here is that for every element of the group and every vertex, we can find an element of the group such that that element acts below the vertex like our given element. So that's what it means for a group to be self-replicating. And that condition is satisfied by the scale group, restriction of a scale group to this rooted tree inside our regular tree. Okay, so we've seen now that if we start with a scale group, we can obtain a self-replicating group. What I want to do next is go the other way from a self-replicating group back to a scale group. So we'll see that there's a precise correspondence between scale groups and self-replicating groups. How am I going for time, by the way? I don't have I can't see a clock here.
25 minutes is left, but we will be happy to hear you as much as you will be able to speak.
Okay, thank you. Well, I don't think I'll need much more than 20 minutes. Let's see. So now we start with a self-replicating group acting on some rooted tree. But now just ignore this this pale tree over here. We just have a rooted tree and a self-replicating group acting on it. And the self-replicating condition says that there's an isomorphism from the group acting below the vertex 0. So this vertex here, the group acting on this subtree here, back to the whole group G, and this is actually an isomorphism between the so stabilizer of 0 restricted to this subtree and the full automorphism group. And we can use this isomorphism now to extend G so that it acts on not just a rooted tree, but on a regular tree, and such that the restriction of this group to this rooted tree is the self-replicating group we started with. So how do we do that? Well, we pull back this automorphism, this isomorphism phi. So we embed our original tree in a larger tree, as if it is now the set of descendants of the one of the children of the root of our new larger tree. And then we can use our isomorphism phi to extend G to a group acting on this larger rooted tree now, such that if we look at the subgroup fixing this vertex that was the root of our original tree, and so we look at the subgroup fixing that, and then we strict to the tree below here, that returns our original group G. So we've now extended G from a group acting on this tree to a group acting on this larger rooted tree. And we label things so that our dot that we had originally, this dot, which was the root of our original tree, I'm now going to think of this as a placeholder, and we're going to add labels. Oh, sorry, let me go back. We're now going to add labels before the dot of our extended tree. Ultimately, our labels are going to be semi-infinite strings, and so this vertex here is going to be labeled by a string of zeros that finish. There's a space just before the dot. Okay, so we iterate this now, to produce our regular tree. So if we do this twice, we now get a larger tree. Here is our original rooted tree. We've now embedded it 2 levels down into a rooted tree, and we label the vertices we've added by infinite strings. Now this root is going to be a string of zeros and then 2 spaces before the dot. Then on level 1 here, we'll have a string of zeros, 1, and then space and our dot. And then we're going to label the other vertices by strings. So our vertices, as we iterate this, will now be labeled by semi-infinite strings, or semi-infinite words, sorry, in all strings in these symbols, where all but finitely many are 0. All right, I was going to write 0. Let's see if I can go back. 0. Okay. So that's going from self-replicating groups back to scale groups. So are there any questions so far? Okay, well, I think I've actually gone a little bit faster than I expected. So let me just go back to this table now. I'm going to say more about can I get rid of this now? I now want to say more about this lower section of the table and the uniqueness of these labellings. So the next part is going to be in 2 sections, actually. So there's going to be, I'll say something, sorry. First of all, I'll say something about the uniqueness of the representation of a subgroup of a totally disconnected locally compact group on tree. That representation theorem that I mentioned earlier there's no uniqueness statement about that. There might be more than one way to represent the group. So I want to say something about that. And then I'll say something about the uniqueness of labeling. Not very much, just ask a question really about uniqueness of the labeling. So first of all, the tree representation theorem. So the construction of the tree in that theorem, if you remember, it depends on this subgroup U double minus, and that subgroup U double minus is defined in terms of the subgroup U tidy for alpha. Now, given an automorphism or an endomorphism alpha, there is no unique subgroup that is tidy for that automorphism, and so there's no unique U double minus corresponding to that alpha. However, the scale of alpha inverse is unique. So the actual tree on which this group acts is unique. It's just T sub Q plus 1, where Q is the scale, and that's some positive integer that's determined by alpha. But U double minus, as I say, is not unique. It's only determined up to some finite index. Now, even if U double minus is unique, or if we happen to choose 2 tidy subgroups U1 and U2, such that the U double minuses agree, even in that case, the tree representation is not uniquely determined, because we can have that that these groups are unique, but the subgroups U1 minus and U2 minus are not equal, or not even conjugate within this semi-direct product. In that case, the representation of U double minus on the tree is, the representations are not equivalent. And so it's of interest to determine when that representation is unique. And that can be described in terms of the action of U double minus on this coset space. So if U double minus acting on this coset space, if this is a primitive permutation group, then this representation via the tree representation theorem is unique. Now, unique up to conjugation by an automorphism of trees, or an intertwining map between isomorphisms of trees. So this primitivity of this action is independent of our choice of U, and if that action is primitive, then the representation is unique. And often that action is primitive. It's primitive, for example, if the scale is small. So if the scale of alpha inverse is 2 or 3, so in other words, if our self-replicating group is acting on a binary tree or a ternary tree, then the action on level 1 of that tree is primitive, and then the action or the representation of the scale group on the tree is unique. So in this case, there's a unique correspondence between, say, tidy subgroups and self-replicating groups. It's not true, however, that self-replicating groups have to have a primitive action on the set of symbols. So this is if X is a set of symbols, they correspond to our vertices on level 1 of the rooted tree, and our self-replicating group has to be primitive on that level 1, so equivalently primitive on the set of symbols of that are used to define the tree. Now here are some examples. The scale groups that I mentioned at the beginning, these scale groups all happen to have primitive actions on level 1, and so they have unique representations on the regular tree. On the other hand, if we just have some finite permutation group acting on X such that the action is not primitive, then the product over the natural numbers of our finite group has more than one representation as a self-replicating group on this tree, defined in terms of the symbols. So there are cases where the self-replicating group does not have a primitive action on level 1. And I think it's of interest to determine just when self-replicating groups do have a primitive action. And in the case where they're not primitive, there might be some way to factor the self-replicating groups in a similar way to that in which finite permutation groups are factored into primitive representations. So that's the uniqueness of the tree representation. Now, what about uniqueness of the labeling? If you think back to what I said about the labeling of the vertices of a tree, it involved choosing some coset representatives. So the labeling depended on this choice of coset representatives. If we chose different coset representatives, we would get a different labeling of the vertices. And so an actual question here is how unique is this labeling of the vertices that is compatible with the scale group action, or the action of U double minus 7 group product alpha. Now, an equivalent question is, if we have a self-replicating group acting on some rooted tree, how many conjugates of that group are also self-replicating? So we can have a self-replicating group acting on a rooted tree that has some conjugate that's also self-replicating, but is not actually the same self-replicating group, because self-replicating groups are defined in terms of a particular labeling of the tree. The same group acting on the tree could be self-replicating with respect to two different labelings. And I think this is the same question as the one about choice of co-set representatives for the scale groups. And I think that's also an interesting question. So here now is, I'm returning now of this picture, and I have talked about, what I've talked about is the this part of the diagram, the relationship between totally disconnected locally compact groups on the scale at one end and self-replicating groups at the other. Now, I haven't said anything about the other parts of the diagram, but let me just say briefly, over here on the right-hand part is something that's of interest to people in College Station, I think, and in particular the growth of groups and the examples constructed by Slava giving rise to the notion of a branch group. Well, that notion also came from the work of John Wilson on just infinite pro-finite groups. So from that we get the idea of a branch group, which is a group acting on a rooted tree, and the self-replicating and self-similar groups come from I think originally from the study of these branch groups. I should perhaps put an arrow here as well. And just in historical terms, I think that things flowed in this direction to come to the definition of self-similar and self-replicating groups. So that's the right-hand part of the diagram here, and the pro-finite groups are, as I said at the beginning, they are exactly the compact totally disconnected groups. So there is some correspondence between this part of the picture and general totally disconnected local compact groups. I haven't said anything about the left-hand side of the diagram here. I don't think I will say very much. Perhaps I will just point out one part, and that is groups acting too transitively on a regular tree. So the full automorphism group, for example, does that, and so do various p-adic Lie groups. They act transitively. They rank 1 act transitively on a tree, and in fact 2 transitively on the boundary. And there's an approach to totally disconnected locally compact groups suggested by Pierre Emmanuel Capras, where he suggests that these groups acting on trees are a sort of microcosm of the full picture of totally disconnected locally compact groups, that many of the features we see in the general case we already see in these groups acting on trees. So I think that's all I have to say. So now I'll thank you for your attention. This is the end.
Thank you, George. Arman, who rules the seminar, you or me?
Say it again.
I'm Arman, who rules the seminar, you or me?
I think better if you.
Okay. Are there questions to George? I have a question.
Yeah.
How much this correspondence describe between self-similar, self-replicating groups? How much it is related to the problem of classification of totally disconnected locally compact groups?
Oh, yes, I think it's a very important part of the classification. There are, so if we just think about this part of the picture for the moment, there are several approaches to studying the structure of these groups, and the scale and tidiness are, tidy subgroups are one approach. I think they are, if we compare with Lie groups, the scale is something, and tidy subgroups, they're something like the eigenvalues in Lie algebra in a Lie group. But there are other important parts of, and I think this correspondence is very important for understanding that part of the picture, that part of the structure of totally disconnected locally compact groups. There are some other aspects to this theory. There's the notion of local structure, which is understanding how the compact open subgroups, so these are pro-finite groups, how those correspond to the global structure. So how local structure corresponds to global structure in these groups. Now the scale doesn't, there should be some connection between notions of scale and tidiness and that part of the structure theory. There isn't a very good connection at the moment, but that connection won't correspond so much to the self-similar and self-replicating groups. So that's another important part of the structure theory that perhaps doesn't correspond. Another part of the structure theory is sort of decomposition theory of trying to take a general group and decomposing it into simple groups or characteristically simple groups. That aspect of the theory also doesn't correspond to self-replicating groups, but the scale does, and I think that self-replicating groups, in a way, it would be great to classify those in some sense, because that would be classifying in a similar sense all the possibilities for the scale and tidy subgroups. But then the next question is, well, given a group, which scales and which self-replicating groups do we see inside that? And related to that is that question that you are and I are interested in, Slava, is whether if we take your self-replicating group, the group you originally constructed, the first one, and the closure of that, so that will give us a closed self-replicating group, that can be extended to give us a scale group. But now I think it's an interesting question whether that group is the stabilizer of an end of a group acting too transitively on a tree. I think that's a question that we don't have an answer to, but it's a very interesting one. But the short answer is it's very close. It's very important, the connection between self-replicating groups and structure theory.
Okay, thank you. Let me make the following remark. So you gave a definition of self-replicating group, like in our theory, Volodya Nekrashevich and me and other guys, we distinguish classes of self-similar groups, classes of level transitive groups, and then self-replicating groups. While you put included in definition of self-replicating group all three properties.
Yes.
So in certain sense, your terminology is different because, yeah. So what you call self-replicating, we will say call self-replicating level transitives. Maybe something like that, but it's not important, of course. Okay.
Well,
yeah.
I guess one reason for doing that is just to save time in the talk. But from what I understood of the definition, self-similar is this condition, B.
Yeah.
And then self-replicating groups are defined to be self-similar groups, so they're already self-similar, but satisfy the third condition. Is that correct?
Correct. Yes.
Well, I usually include condition 8 in self-replicating.
Condition A as well.
Volodya, okay, we disagree with Volodya in some definitions. Okay.
So Yeah, so
Other questions?
Yeah, I had a question. So if you have an automorphism of a TDLC group, you get this scale group
Yeah.
from U double minus, but then you
Yeah.
also have a scale group from U double plus.
yes,
So, so the scale groups sort of come in pairs if we're coming from automorphisms of TDLC groups. Do we know anything about the relationship between those two scale groups?
Depends what you mean by you know anything about the relationship. In general, there's no relationship because one.
Yeah, I mean, one of them could be trivial, but I mean, you know, if they're both sort of big in some senses, that there's some way that they have to interact.
I think that's an interesting question, and I do have some questions about that. For example, well, okay, suppose our group is simple. Suppose our group is topologically simple, then it's unimodular, and in that case, the scale of alpha and the scale of alpha inverse are the same. And so the groups that they are acting, the scale groups are the trees that the scale groups are acting on are the same. And we could ask for trying to get some correspondence between, and there is some intersection between U double plus and U double minus. And so we can try to ask for some sort of compatibility between the actions and maybe try to get them both acting on the same tree, but with different ends, which is exactly what does happen in this case, right? If we have a group acting too transitively on the tree, then if we take some alpha in our group, well, we're not called alpha, I'll call it G now. Take some group element, then the G fixes, so G fixes two ends. Let's call them minus infinity and infinity. And there are two scale groups and they're acting on the same tree. Now, that's if we already have this situation where we have a group acting on a tree. And it's an interesting question about, well, if we don't already have this, then how do these two scale groups interact?
Okay. Other questions? If not, the seminar is finished. Thank you, George, very much for your wonderful talk.
Well, thank you for the opportunity to speak.